Good morning, kids. Today I'm going to talk to you about slope fields. It's a different way to look at a differential equation. We did differential equations earlier this year, and now we're going to look at these slope fields. First of all, I want to make sure you have the right papers. You'll need this paper that looks like this, and then you'll have a packet that starts with this page, and it's got like 4 or 5 pages in it at least. And then you'll have another packet that starts with this page. It says page 7 of 13, and this is what the first problem on it looks like. That'll be your homework packet. Alright, so hopefully you can get your hands on all those things. Maybe pause the video while you get all those things out of the file cabinet, and then I'm going to move forward. So today, like I said, we've done differential equations before. This time, we're going to look at the way we write them. Okay, so one way to write dy dx is as some function of x and y. One way is to write it as y prime equals some function of x and y. And the other way is to say the derivative of y is equal to some function of x and y. So in order to check a solution to a differential equation, we always need to plug in the derivative and y of x into the original equation. That's just a little review. So today we're going to look at a slope field, which is the graphical representation of all the solution curves for a differential equation passing through a point and having given slopes. The way we draw a slope field is by making short line segments of the slope, that is whatever y prime is, at selected points. So you actually plug x and y into y prime, and then you draw a little line that has that slope at that point. And the slope field will always give you the general shape of all the solutions to a differential equation. So that's all I'm going to cover on this page today. The Euler's method on the bottom I'm going to cover next class. So now we come down to the first example. This is a slope field. It's a series of little tiny slopes. What you'll see here is you have various different slopes on your picture here, right? And for example, and if you follow the slopes, they will take you right to the next slope. So for example, this one's not very steep, but if you follow it, it takes you over to here and it gets steeper. And if you follow that, it takes you to here and it gets steeper. And it's not very precise, so if you're into precision, you're probably not going to like this. And then if you follow it back this way, it looks like that. Alright, so there's one solution to this slope field. Now, you know how differential equations, when you solve one, you get y equals blah 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 plus c. Well, you see, these are all the different constants you could have. So if I have a slope field down here, that means my constant was negative, okay? And in this particular slope field, it appears that all of the slopes end up going towards negative infinity. As you tend towards negative infinity, our slopes seem to go towards 0. Where in this, if you go towards positive infinity, this particular slope tends towards negative infinity. This one up here goes to positive infinity. So it depends really what you pick out as your initial value. Now, what do you do with these things? Well, this is a slope field of the differential equation dy dx equals 2x. Now, if I solve that differential equation dy dx equals 2x, what do I get? Well, I get dy equals 2x dx if I multiply both sides by dx. And then when I integrate both sides, check it out. I get y equals x squared plus c. Well, if you look at these slope fields, check it out. We've got a bunch of parabolas. You see them? These slope fields are all different parabolas. And these, of course, where we cross the axis, turns out to be our constants. Okay, so there's a few different examples of dy dx equals x squared plus c. So for example, this one would have a constant of about approximately 1.5. This one would have a constant of approximately 2.5 maybe, and this one might have a constant of negative 1.3. I'm just guesstimating, obviously, of where it crosses the axis, but that constant will determine which path you have. So this is just a graphical representation of our solutions that actually shows all of the possibilities for constants. Okay, so that's what a slope field is. If you look at the next slope field, you can almost guess what this slope field is, what the solution is to this differential equation. We have dy dx equals negative x over y. Now, check it out. What does it look like we have a bunch of here? Well, certainly you can see we have a bunch of circles. I am not good at this, right? So I am not good at drawing pictures like this, so please bear with me. But these are all circles, and depending on what the constant is, you get different things, okay, for your solution. So let's check this out. If I were to solve this, all right, differential equation, I would get multiplying both sides by y and dx. I would get y dy equals negative x dx. So I would get, if I integrate both sides, 1/2 y squared equals negative 1/2 x squared plus c. And then if I go ahead and finish this, moving it over to the other side, I get, and I can multiply the whole thing by 2. If I multiply c by 2, I still get another constant, right? So I get, moving the x squared to the other side and multiplying by 2, x squared plus y squared equals some other constant. Let's call it c1. Well, what's the constant? Well, the constant is the radius of the circle. So, for example, check this out. This would be a circle with a radius equal to 1. So your constant here would be 1. So, very interesting to look at how differential equations relate to their slope fields. Now, these are sketches, and I know there are some of you who really, really loathe when things cannot be done exact, okay? And these slope fields, I mean, you sort of have to guesstimate where you're going. You have to follow the path of the line. First one says, sketch the solution curve with the initial conditions of y equals 1 when t equals, this should be a 0, not an O. So y equals 1 and t equals 0. What does that solution curve look like? Well, if 6 is up there, okay, I would say that 2 is about here, and I would say that 4 is about here. Alright, so you're looking for the coordinates y equals 1 when t equals 0, the coordinates 0, 1, right? This gives you coordinates 0, 1. So you go to the coordinate 0, 1, which would be about here. And then you sketch out the slope field. Well, if you take this backwards, the slopes become more steep as you go forward. And if you take it forward, they become less steep as you go forward until at 2 you hit this flat line, this 0 slope. And if you have a 0 slope and you follow it, it just takes you to the next 0 slope. So that one ends up looking like that. The next one says y equals 0 when t equals 1. So that would be, oops, I circled the wrong thing there. I should have circled y equals 1 and t equals 0 for 0, 1. All right. And then y equals 0 when t equals 1, well, that's 1, 0. Let's see where that goes. All right, so we'll come down here. We'll go to the point 1, 0. Okay, well, if this is 4, then this is about 2. And this is about 1. So if I'm following there, what happens? Well, as I go down, they become more steep, my slopes, and as I go up, they become less steep until, again, you end up right at 2, where you end up at a flat spot. What does that look like? Well, it looks like a horizontal asymptote to me, and that's exactly what it is. Okay, let's look at the third one. It's y equals 3 when t equals 0, so that would be 0, 3. And if you look at this one, that would be up here, 0 over 3 up. And if I go up towards negative infinity on the t-axis, it becomes more steep. If I go towards positive infinity, it becomes less steep until finally, what happens at 2? Well, again, we flatten right out. Everything as I approach positive infinity, as t approaches positive infinity, what happens? Well, as t approaches infinity, y approaches 2. And what else happens? Well, if y0 is greater than 2, if your initial y value is greater than 2, and t approaches negative infinity, then y approaches, well, what happens? Let's look at it. As I approach negative infinity, my y's approach positive infinity. And if y0 is less than 2 and t approaches negative infinity, well, that's here. If I start out less than 2, then I'm going that way. I'm going to be, my y will approach negative infinity. Okay, so you're looking at the long run behavior. When it says long run, that just means as t approaches infinity or t approaches negative infinity. That's what long run behavior is talking about. Going to the next page, just some more examples of slope fields. Even though the family of solutions for a differential equation is shown by a slope field, a solution curve exists and is unique provided we're given an initial point. So in this one, again, you just follow the path that is given you. So in this one, for example, if I pick this point, right, if I follow the path, what's happening with my slopes is it looks like that, and here it looks like this. Alright, so depending on where I am on the curve, my solutions are going to look different depending on what that constant is. Again, where do I start? And then I just follow the direction that these little lines take me. And then I follow the direction that the next little line takes me. Next class we'll be learning Euler's method, which is really the same type of thing as this, except we do it with numbers. You'll have a slope that takes you to the next slope based on adding it to your y. Okay, so now let's look at this matching problem. And the way we do these matching problems to match a slope to the slope field is you've got to figure out three things. When is it 0? When is it positive? I should have put positive, not plus. And when is it negative? That's going to give you an idea of which choice to make. All right, so let's look at the first one here. Y prime equals 1 plus y squared. So we've got to wrap our head around the function 1 plus y squared. Is that function ever 0? Will y prime ever be 0? No, it's not ever going to be 0. So let's say never. So already we're looking for something that is never going to be 0. This slope will never be 0. You will never have any flat lines in this graph. Okay, so let's look at our next question. When is our slope going to be positive? Well, guess what? 1 plus y squared, I don't know anything I can put in there and get a negative number. So it's always going to be positive. So that gives us a big clue. We need something that has always positive slopes. So as I go from left to right, remember we always read slopes from left to right. Okay, you know I always read slopes from left to right. Well, I'm going to have positive slopes from left to right. So that's going to give me a pretty good idea of which one of these to choose. Let's look. Are there any of these graphs that have all positive slopes? Never anything that goes down from left to right. Well, if you look at number 2, guess what? It's always positive. If you look at it, there are some very steep positive lines, but basically they are all positive slopes. So number 2 would be the answer to part A. Let's look at part B. Y prime equals x. Well, when is this 0? Well, it's 0 when x equals 0. When is it positive? Well, it's positive when x is greater than 0. Okay, so that is to the right of the y-axis. And when is it negative? Well, it's going to be negative when x is less than 0. So we're looking, it's going to be negative to the left of the y-axis. Well, that gives us a pretty good idea of what's going on. So 0 at 0, well, x is 0 on the y-axis. So I'm looking for something that has slopes of 0 on the y-axis. Well, there's 2 spots that happens, here and here. Well, you can almost tell number 4 which type of function that is by the way the curves go, right? You can tell that that's going to be a trig function. So let's look at number 6. Do we have 0 at 0? Yes. Do we have slopes that are positive to the right of the y-axis? Yes, we do. Do we have slopes that are negative to the left of the y-axis? Yes, we do. So it's number 6 for B. Next one, y prime equals sine x. Well, let's double check, but we have a pretty good idea of where this is going to be. Okay, so y prime equals sine x. Is it 0 ever? Yes, it's 0 when x equals 0. It's also going to be 0 at every multiple of pi. So x equals 0, x equals plus or minus n pi, where n is an integer. And then is it going to be positive or negative? Well, let's just think trig. Okay, that's really all you have to do is think trig. It's 0 at x equals 0 and at multiples of pi, so you can see that in number 4. You also see a trig shape. So number 4 is the answer here, and the antiderivative of sine is cosine. So that should be some sort of cosine graph. Well, it's actually negative cosine. It's a flipped cosine graph. All right, y prime equals y is the next one. It's 0. When y equals 0, it's positive. when y is greater than 0, which is above the x-axis, and it's negative when y is less than 0, which is below the x-axis. Beautiful. So that's what we have. So now let's go ahead and take a look. It is which one has zeros at y equals 0 or on the x-axis. Well, let's see. We've already used 6, we've already used 4, we've already used 2. So we're looking for slopes of 0 on the x-axis. It appears that that only happens in one place, and that would be choice 1. Let's double check. Do we have positive slopes above the x-axis? Yes. Do we have negative slopes below the x-axis? Yes. So D is 1. Y prime equals x minus y. Well, when is this going to be 0? Well, set it equal to 0. 0 equals x minus y. So x equals y. This is going to be 0 when x equals y, or y equals x. So look along the line y equals x. We just used 1. We only have 2 left. So if we look along the line y equals x, which one of these appears to have a slope of 0 always on the line y equals x? Well, check it out. Here it is. See all those little slopes of 0? So that's going to be number 3. And then hopefully this would be 0 equals 4 minus y if we wanted to figure out when it's 0. So 4 equals y. So we're looking for this to be 0 when y equals 4. That's kind of a strange place for it to be 0, so hopefully you just find that. And right here, we don't know that this is 4, but we can assume that this is 4. It's a positive number. We have 0 slopes at a positive number, so that's going to be 5. So this is it's like a little puzzle basically when you try to figure these out. So good luck with those. You'll have some of these matching activities on your homework, and I think these are the most important of the activities that you will do. So good luck with that. Now I want to show you your homework. It's the packet that says homework on slope fields. It says exercises and problems for section 11.2, and I have a lot of the answers here already on mine, but basically it's 1 through 10. I'm pretty sure that number 9 is the problem we just did. It is. So you can skip 9. 1 through 10 all, skip number 9. That is your homework for next class. It should be fairly quick. So enjoy, and I'll talk to you soon. Bye.